Hello everyone, my name is Mohammad Sarmad Mir. I am working as an early stage researcher in Marie Curie IT project Enlighten at MDI Networks Spain. Today I will present you our work with title RGB LED bulbs for communication, harvesting and sensing. This work is done in joint collaboration of MDI Networks Spain and Lightp. In the last decade, the IoT market is rapidly growing. IoT devices are interconnected and exchange information. Mostly, the IoT devices sense the environmental parameters such as temperature, humidity, and or motion and communicate it to the infrastructure. They require energy to perform these tasks and a medium to communicate information. In parallel, VLC has extended its way from research to market products. Visible light communication is projected to get large market share in next few years. VLC can utilize passive lighting infrastructure and also LEDs are energy efficient. VLC is emerging as a complementary technology to RF to enable a vast deployment of IoTs. In a typical VLC system, we have a VLC transmitter, which is a light source, normally white phosphorus LEDs. The problem with that is we don't have any control on hue. As a VLC receiver, we have many options. We can use photodiode or solar cells, but photodiode is cheap, but it is not pervasively deployed. On the other hand, solar cells are expensive and less sensitive to light change. We can also use image sensors, which is expensive, and not every device is equipped with it. And we can also use LEDs as a receiver, which are cheap and passively deployed. So we can, the use of LEDs as a transmitter and a receiver can help for vast deployment of IoTs. Do you know how light color impact those who are exposed to it? For instance, blue light disturbs the sleep by suppressing the secretion of melatonin in body. Also, red light can help the growth of the plant. Different light temperatures can be used according to the place. For example, cool light is ideal in hospitals. Neutral lights brighten the colors, so they are ideal in museums and art galleries. Warm light can help to wound healing and hair regeneration. RGB LEDs can be used to adopt colors according to the application. They have multiple LEDs in single enclosure, normally red, green, and blue. They give us full control on hue, so we can select any color by giving different voltages to the RG and B terminals. They can be used as multiple communication channels using wavelength deviant multiplexing. Also, in this curve on the right bottom side, you can see that we have wider curves, which are filters, low-cost filters, and we have a narrow curve, which are from the RGB LEDs. So we can see that by using LED, we have very less intercolor interference as compared to low-cost filters. But the cost of RGB LED is higher than the white LED. So the question is, how we can provide enough added value to justify their cost. Are there any other applications than illumination? In previous work, we can see that people have tried to use RGB LEDs to get a two-way communication. For example, in this work, they are using net-to-net combination and get a very low data rate and with low range of communication. There's other work in which they have used different transmitters, green as transmitter and yellow as receiver to get 49 kb per second with a very short range. There are some works in which they are using the discrete LEDs like separate green, red, and blue, and with limited combinations to see their effect on harvesting. But all these studies are done separately and no holistic view is available. So in this work, we are exploiting RGB LEDs for IoT applications. For communication, we are having a LED as transmitter and LED as receiver. And we are also working on harvesting to see which wavelengths are optimal harvesting, which maximize the harvesting with the same power. And also we are presenting a low cost sensing applications in we can detect the variation in wavelength by using the LED as receiver, because when light is incident on the LED, that photocurrent is generated proportionate to the amount of illumination. So we can detect the variation in wavelength, for example, to measure the health of a plant. So now I will present the design and implementation for all the scenarios, communication, harvesting, and sensing. We started with the selection of LEDs. There are multiple LEDs available in market. In most of the recent work, they are using a small low power pin LED, which can be a good option for communication, but they cannot be used for illumination because their intensity is very low. So we have chosen LEDs which are around forward voltage of 3 volts. And we made a fair comparison between these 3 LEDs to choose the best one for the communication in terms of bandwidth and range. So we started with providing the same electrical powers to these LEDs with the RS transmitter, green as transmitter, and blue as transmitter, and all the combination we tested for receiver. In this table, you can see that we have measured the path loss in dBs, and also we have presented the bandwidth in kilohertz, which is given in the brackets. And some LED combination give very low bandwidth, so we presented it with a dash. So with this experiment, we come to know that the LED3, which is a pre-MC4, it performs best in terms of range and data rate and responsivity. So here I present the schematics for our system. We are using MOSFET-based drivers, and we are using potentiometers to control the current in each and every branch. For a receiver, we are using a transimpedance amplifier to improve the bandwidth of the system, voltage amplifier to increase the received signal, and we are using a 1-bit ADC, we are using comparator. And there are multiple high pass and low pass filters to filter out the noise from ambient light, which is normally at a low frequency. Here we can see that in transimpedance amplifier, we have a RF, which is a feedback resistor. It has direct effect on the bandwidth and the strength of the received signal. So in the evaluation, I can show you the results that we obtained. So for communication, we can see the selection of RF is important. By selecting the bigger value of RF, we get a greater peak-to-peak voltage. And here you can see that we have frequency on x-axis, peak-to-peak voltage on y-axis. And with RF, with the highest value of RF, we get the maximum peak-to-peak voltage. But for bandwidth, it is opposite. For lowest value, which is 200 kilohertz, we get the maximum bandwidth. We have used the red LED as transmitter and red as receiver, which gives the best communication range. And we get the throughput of around 50 kilohertz, which is 100 kbps. We can see in a green line here, which is the 50 kilohertz signal. The solid one is without any background illumination, and the dotted ones are with the 600 lux background light. And we get the range of around 3.5 meters by using red LED as transmitter and red as receiver. For harvesting, secondly, we evaluated and we tested 36 different combinations in the portion of 50 milliamperes. The total current is constant to 350 milliamperes, and we use different values of IR, red current, IG, which is the current in the green LED, and IB, which is the current in the blue LED. And as a receiver, we use solar cells with and plus harvester and to calculate the harvested power. And from this graph, we can see that we generated different colors to cover all the chromacity diagram. And then from the results, we can see that the blue wavelength, the red wavelength performs best as compared to blue and green. And the performance with by illumination with the green LED is the worst. So we extended this work to sensing application, which provide a very low cost sensing solutions. We can use RGB LED with a voltage follower and some microcontroller for analog to digital communication. And we tested how we can identify different sources. We tested with fluorescent light, sunlight, and white LED. And we can see that with the and we evaluated it with for fair comparison, we give the same illuminance to all of the from all of these three LEDs, and on receiver side we use the RGB LED. So when we can see that the blue LED performs best in case of white LED, it is not very responsive, but when it comes to sunlight, we can see a voltage change of around 1.7 volts. So for detection of sunlight from other light sources, we can use blue LED, maybe, and as it is more sensitive to ultraviolet band. Also, the other application that we demonstrated is the health of a plant. We took a plant and because the color of plant changes in case of disease and dryness, we didn't water it and let it dry. The color of the leaf changes with different days. We can see from day 1 to day 8. And then we illuminated them with RGB lights and measured the response by using LED as receiver. And we plotted them the best combinations on all days. And we can see that there is a significant difference of around 0.51 volts when we use red to red combination, and green to red combination gives around 0.46 volts. So by using the LED as transmitter and receiver, we can use different color combination to identify the health of a plant. So there are different insights from this work. For example, we can use red to red LEDs for best communication in daytime, in nighttime. And then the red wavelengths are best for energy harvesting, and also for night sleep. If it is much better than having a blue light. So at the time of night, we can switch off the blue light and increase the percentage of blue light red light. Also, blue light works best to detect the sunlight. So we can detect sunlight in order to change the color of a transmitter and to optimize the harvesting. And for plant sensing, red as transmitter and receiver work best, but as we are using red for communication, so we can use green as transmitter and red as receiver. And at night, obviously it is desirable to reduce the blue light emission, so we can reduce the content of blue light in the time of sleep. And these functions are performed in parallel, and we can do the communication and sensing at the same time. So by adopting to the two different applications, we can use RGB LEDs in different combinations as per requirement of the situation. So just to conclude, can say that the RGB LED has the potential to enable different applications beyond illumination communication. We can use them for bidirectional communication, for optimized harvesting, and different low-cost sensing applications. These systems help to increase the value to RGB LED and accelerate adoption to illumination market and rapidly growing IoT market. Thanks for listening to the presentation. I'm happy to take any questions.